Hello and Assalamu alaikum everyone. My name is Arsalan Farrukh and I teach math and physics. In this video, I will discuss how to perform the process of integration by parts. But before, let's have a look at where the formula comes from. So you might have already seen this formula of the product differentiation, that is if you have to differentiate the product of two functions, which is u times v, then that is equal to u dv by dx plus v du by dx. This formula actually comes from the first principle method. Right now, our focus is to have a look at the formula of integration by parts. So let's see how we get that. First of all, from this formula of the product differentiation, I will cross multiply dx on the other side. And when I will cross multiply dx on the other side and I put integral on both sides of the equation, I'll have a term which is integral duv, integral u dv by dx times dx, and integral v du by dx times dx. Here, the integral and differential will cancel out and you will get u into v. And if you will rearrange this formula by shifting v du by dx on the other side, so you will get yourself integral u dv by dx into dx is equal to u into v minus whole integral of v du by dx into dx. This is the formula that will be provided to you in the formula sheet. But we can simplify this formula a little more so that we will be able to apply it more effectively. So if I cancel dx over here and here, the formula will turn into u dv's integral is equal to u into v minus whole integral of v du. So this formula is going to be provided to you in the formula sheet, and you can simplify this formula into this form to apply it more effectively and more easily. Now, why is this formula useful? This formula is useful because if you are trying to find out the integration of product of two functions and you suppose one to be u and the other one to be dv, and you are having a bit of a trouble in sort of integrating u, what this formula does is that it gets the u out of the integration sign. So you don't have to integrate u anymore, although you will get the derivative of u inside the integral sign, but that might be easily integrable. So let's see how we apply this particular formula. But before you apply the formula, just remember this Liate principle method, which is your order of preference for u. L stands for logarithmic, A stands for algebraic, T stands for trigonometric, and E stands for exponential. So if you see a function inside the integral, your first preference to suppose u would be log. If there's no log function, then your next preference is an algebraic function like x square or x cube or anything of that type. And if you don't have a log or algebraic, then obviously your preference order is going to be of trigonometric. And if you have none of these, then your preference order for u is going to be exponential function. Now let's see few examples. Let's say I have to integrate a product of x sine x. I can see it's a product of two functions, and I see that there is a possibility of using the integration by parts formula. So when I look at the Liate principle, I have one function x which is algebraic and the other function sine x which is trigonometric. So my preference would be algebraic function as u. So I will take u as x and I will take dv as sine x dx. Once you have supposed what is going to be u and what is going to be dv, there's going to be one thing always constant with this process. Your formula is integral u dv is equal to uv minus whole integral of v du. So if you have made a choice of u, then you know that to apply the formula you need to have du. So always you are going to differentiate the function u to get du. Similarly, if you have supposed dv, and dv is always going to be supposed with a product of function with dx, then to apply the formula, you also need v. And if you have supposed dv, then you always need to integrate to get v from there. So one thing is always going to be there. Once you have made your choices of u and dv, you will always differentiate u to get du, and you will always integrate dv to get v. So if u is equal to x, I differentiated this equation, I got du by dx is equal to 1, or I got du as dx. So I know that when I'll be applying the formula, in place of du, I can write dx. Similarly, since I've supposed dv as sine x dx and I need to plug in v, that means I'm going to have to integrate the dv equation. So when I integrate both sides, the dv integrates to v, and I must know that the integral of sine x is equal to negative cos x. So I've gotten myself v as well. Once I have u, du, v, dv, I'm all set to use the formula. So the formula goes like u v minus whole integral of v du. So in place of u, I'm going to write x. In place of v, I'm going to write minus cos x. So my first term is going to be product of minus x cos x. Then I have a minus sign of the formula, an integral sign, and then I put v again, which is minus cos x. So in place of v, I have put minus cos x. And then I have to put du, which I've just found out as dx. So du comes out to be dx. After coming to this particular point, I will always see, I will have another integral, that is how the formula is like, and I will have an integral here, but I will always see that this integral must be easier or simpler than this integral. So I will be able to integrate it more easily or more effectively as I can do in this case, because I take minus outside, it becomes plus, and I will have only cos x to be integrated here. So the integral of cos x is known to be sine x. I can directly plug that in here, and I have performed my process of integration. Now, if it was a definite integral, then I will obviously put down the limits and evaluate it. But since this is an indefinite integral, so I will add a constant after integration. Let's have a look at another example. I have to integrate x cos half x dx. I again recall my formula, which is u dv integrates as uv minus whole integral of v du. I had to make a choice of u and dv, and I recall the formula Liate principle, and I will identify that my preference for u is going to be algebraic. So I suppose u as x, and I find du from there, and I will suppose dv as cos half x dx, and I will integrate that, and I will use the formula of integration, and I'll know that since there is a half as a coefficient of x, so that will divide the integral result as per the formula. So this becomes 2 sine half x. After getting myself the du and v, I will apply the formula of integration by parts. So this is going to be u into v, that's going to be this times this, minus whole integral of v du, that's going to be this times this. So that's going to be 2 sine half x times dx. And then I will see that this is an easier integral. I will be able to integrate sine half x, that comes out to be cos half x upon half, and I'll simplify that, and this will be my whole integrated result. Let's have a look at another example of algebraic and trigonometric. I suppose du as x and dv as sec square x dx. The derivative of u is going to be dx, and when I integrate sec square, I can directly look at the formula. The formula of integration of sec square is tan x. So I will get myself x tan x as u into v minus whole integral of v du would be integral of tan x. For tan x integration, again I have to recall a formula of integration, which is integral of u prime, that is derivative of a function divided by u, the function itself, is equal to ln u. So I can rewrite tan x as sin x over cos x. I can see the derivative of cos x is minus sin x, so I introduce a minus sign by multiplying a minus outside as well, and then I can see that the cos x derivative is here, so I can apply this formula directly and it will be ln cos u plus c. So, and this came out to be x tan x, and this is going to be my overall integrated result. Let's have a look at another example of algebraic and trigonometric function. U is x, dv is cos square x dx. I have to recall again that cos square x is a function that I cannot integrate directly. I'm going to have to apply the double angle formula. So I know that cos 2x is 2 cos square x minus 1. I can rearrange it to get myself cos square x as cos 2x plus 1 divided by 2. And then I will integrate it. I will get myself v. I've already gotten myself du, and then I can use the formula. So this is going to be u into v minus whole integral of v du. When I open this up, I get one integration of sine 2x, another integration of x that can be integrated directly, and I will get myself overall results. Sine 2x would integrate as negative 1 upon 2 cos 2x, and x would integrate as x square upon 2, and that can be simplified into this final result. Now let's have a look at another example where we apply integration by parts, but it doesn't completely solve the process for me, so I'm going to have to repeat that. Like, I have to integrate x square cos x dx. I've supposed u as x square. According to my preference of Liate principle, I got u as x square and dv as cos x. I differentiated u, I got du as 2x dx, and I integrated dv and I got v as sin x. And once I applied the formula, I will notice one thing, that this integral is still a simplified integral than I had in the original integral, but this is again something that I cannot directly integrate. Then I will see that I have to apply integration by parts once more. So I will just consider this part of the integral, which is x sin x, and perform the process of integration by parts again. U as x, dv as sin x, I differentiate u, I integrate v, and I apply integration by parts formula, and I got my result. Now this thing is the integration of this thing, hence the replacement of this thing in my original integral. So I copy this down here. I can see x square sine x minus 2 from original, and in place of integral I can substitute this back directly, which is minus x cos x plus sine x. And once I see that I performed my entire process of integration, I can now add a constant of integration over here. Let's have a look at another simpler example. I have to integrate x e power minus x dx. I have considered u as x. I've considered dv as e power minus x dx. I've differentiated u to get du, I've integrated dv to get v. You can see this is u into v, and then I will apply the formula minus v du. That's going to be minus e power minus x with the minus outside. So that simplifies to plus integral of e power minus x dx. And I can see that this is an integral which can be integrated directly in one step. So the integral of e power minus x would be minus e power minus x, and that gets me the overall integrated result. I could be required to do the same thing repeatedly as well, because if I have x cube e power x and I apply the integration by parts formula considering u as x cube and dv as e power x, and I simplify that, then I know that du is going to be 3x squared dx after differentiating. And once I put it in this place, this is not an integral that I can directly integrate in one step. But I will acknowledge the fact that this is simpler than the original integral. That suggests that I am on the right track. So what I do is that I continue on with this, just consider this part of the integral, and again apply integration by parts onto that. I repeat the process, I got the result, and then again I got an integral which is simpler than the previous one, but not something that I can again integrate in one step. So I again just consider that part of the integral and I integrate that. In that integral, I have to integrate ex, which could be integrated directly. So once I have integrated this thing, I'm going to plug that back into its place, and I will get the second step of integration. And once I will get this, this is what I get over here in this place, then I'm going to plug this thing back in expression 1 and I will get myself the overall result of the integration. And once I've gotten myself the overall result of the integration, one last thing I have to do is to add a constant of integration. Now, for ln functions, you have to recognize that you don't have a formula of integration of ln x. You have a formula for integration of 1 over x, and that integrates to ln x, and that may confuse you sometimes, but you don't have a direct formula of integrating ln x. So if you ever get an integral where you have an ln function, then you know you must be using integration by parts. So if you have to integrate ln x, and your choice according to the Liate principle is always going to be ln as u. So you suppose u as ln x and you suppose dv as dx. You differentiate du to get dx and you integrate dv to get x. And once you've done that, this is u into v minus whole integral of v du. And you see that this integral is quite a simplified integral which can be integrated directly. So I will integrate it directly and I'll get my overall simplified result. This can be done with some product with ln as well. So if you have ln with x cubed, so you take u as ln x and dv as x cubed dx. You differentiate this, you will get yourself du, you integrate this, you will get v, and once you put all of this into the formula, you would realize that this integral has gotten rid of ln function and hence can be integrated directly. So you integrate this, you will get yourself the answer of the integral, and this is going to be your overall simplified answer. Let's have a look at one more slightly complicated example. I have again ln function over here, so I'll suppose u as ln x whole square and I'll suppose dv as x dx. I differentiated it, I still got a ln function in that, because in process of differentiation I'll apply the chain rule principle. I'll multiply by 2 as a power, reduce power by 1, then I will differentiate the base again, that differentiates to ln x. Then I will integrate dv and that comes out to be x squared divided by 2. And once I've gotten myself du and v, I can apply the integration by parts formula, u into v minus whole integral of v du. But this is where I'm going to realize that even this integral has a ln function in it. But it must be noticed that this ln function is simpler than the original one. So I will continue on with this and realize that I have to perform integration by parts once more here. So I will just consider x ln x dx. U will be ln x and dv will be x dx. I differentiate this, I integrate this, and then once I apply integration by parts onto this part, this is being copied from here as it is, and this is being integrated, which I've directly put in over here. And when I integrate this, I realize that the integral that I get over here has no ln function in it and can be integrated directly. So I integrate it directly and I will get myself an overall result of integration. Now there's a particular type of question which is less likely to come in exam, but I would suggest you to go through this kind of question, which would be helpful for you in case if there's a difficult question coming your way, which is that you have a product of exponential and trigonometric. Again, going by the principle of Liate and knowing that you have a trigonometric function and exponential function, so your u is going to be a choice of trigonometric function. So u will be cos x and dv will be e power x dx. You differentiate this to get du, you integrate this to get v, and you come to this point where you have solved this integral. But then you would realize that this is something that is not simpler than the original integral. If you can sort of memorize this particular situation where you have a product of exponential and trigonometric and it does not simplify, that will be a situation where you have to do a cyclic integration. I'll explain you through, but what you do is that you don't stop here and then you again apply integration by parts over here. So when you again apply integration by parts here, you have u as sine x, you have dv as e power x dx, you have differentiated u, you have integrated dv, and you have gotten yourself du and v, and you can apply the integration by parts formula. So you will see that once you come to this point, this integral is the same as the original integral you had in a question. And you would also realize that this will just keep on forever and ever, because it'll just keep on changing into e power x sine x and e power x cos x. But you can also realize that since this is equal to the original integral, you can write that my original integral is equal to e power x cos x plus e power x sine x minus I, the original integral. And then I can rearrange this equation to make I the subject of the equation. And that is where I will be able to solve myself an unknown integral. So what happens is that you find the required integral in terms of the same integral, and you rearrange it to make that unknown integral the subject of the equation. And once you have obviously performed your integration steps and you've gotten yourself a final result, you will add an arbitrary constant as constant of integration. So guys, this is all that you need to know regarding integration by parts. If this did help, I would really appreciate if you would give a thumbs up and also subscribe to my channel. Thank you.